Okay, today we're going to talk about infinity. And that's going to be really important for us to discuss because I've set up sort of an impossible problem. If you've been following along with my modules here that I've been developing to teach the holistic adjustment technique, to sort of introduce this new method to the appraisal community, we need to talk about how to deal with that. Last time we talked about trying to deal with that in a deterministic way, we had this flat valley problem. So we have all of these, potentially um, roughly equal solutions. And so mathematically, what we're talking about is infinity. So let's look at two types because we're going to need to deal with both. And I'm going to talk about the strategy for that. The first is unbounded, and that's infinity as you've probably always heard it. Numbers that keep going larger and larger, and if you flip the sign to negative numbers, they keep going smaller and smaller. You can always add one, and a number will get larger. So that is the way you've probably always thought of it. And then we need to recognize that there is continuous infinity between two integers. So if we take a 1 and a 2, like in this example, you can keep uh, zooming in, as it were, smaller and smaller to smaller subsets of this number. You can think of this like half-life in science when you talked about you probably learned about different radioactive materials, and they have a half-life. They will in a certain number of years, there'll be half as much and then half as much as that. And so you can keep taking that down to smaller and smaller portions infinitely. You can always take a number and divide it in half. So that's continuous infinity. So today we're going to talk about this unbounded type of infinity. So if we have a a problem like I've defined in terms of the complexity of real estate markets, the inherent levels of uncertainty that we have to deal with. We have this problem of a high number of potential solutions, an infinite number in some cases, depending on your data set. So how can we deal with that unbounded infinity? Well, now is where we can take that idea of having an unbounded number that we're dealing with, and we can bound it through Bayesian reasoning. So we're going to talk about constraints. So what's Bayesian reasoning? It's essentially just it's a framework for dealing with prior belief. We're not entering any appraisal problem unless it's your first day on the job. You're not starting with no prior beliefs. You have likely encountered whatever problem you're dealing with before. So if you've got an assignment and you're looking at your set of comps and you're saying, okay, I have real market driving differences in views and lot size, gross living area, room count, and amenities. I've got I've got several variables. The way those variables interact, the number of variables relative to my number of comps, is creating this infinite number of solutions. But I have prior experience and knowledge on all of those property elements. So I say all the time, maybe it's because I'm from Texas, this isn't my first rodeo. I've seen a traffic influence before. I have studied a traffic influence before. So I'm coming in with a level of prior knowledge. So it's important to realize that that is really helpful in bounding infinity. Whether it's prior knowledge or just logic, I can say, well, my gross living area adjustment, in this particular assignment, it can't be zero. The market does. The shape of my market is such that square footage has value, and so my prior belief is that the gross living area adjustment has to be greater than zero. Well, what I've just done is I've constrained infinity. So there's a whole lot of numbers that cannot exist in my solution. Same thing, there has to be a logical upper end to that. If I'm looking at my comps, say they're all, selling at $400 a square foot, and that's the average price per square foot with land and everything. It's like, I know it's going to be something less than that. Well, okay, I've just now uh, put a constraint, and I've dealt with infinity below zero and infinity above 400. That's really helpful. And so what we need to realize then is that we're taking that prior belief and we have to update it with new evidence. If we don't do that, what we're doing is we're just taking our prior beliefs and we're codifying it. We might as well just make our adjustment worksheet, hand it to the next trainee, and perpetuate that practice, because there's no reason for new evidence. So I already know what those adjustments are. You apply them and move along. Well, that's not really helpful either. We have to be willing to admit that our prior beliefs um, are just that. They're beliefs, and they need to be flexible to being updated by new evidence. So my prior beliefs in terms of my gross living area example, it's not going to be 0 to 400. Like I say, it's not my first rodeo. Maybe I've seen that the the best explanatory adjustment for that be, say, between uh, 50 and 100 for a particular assignment. Okay, how confident am I in that? Well, so I need to be willing to say, well, I guess there's a way that maybe the data could be formed that maybe a smaller adjustment could be conceivable, or maybe a larger one. So I've got some room there for expanding my beliefs based on data. But there's an interplay, there's a tension there between the two, and that's really good to have that, to be aware of it, and to essentially move forward holding both of those things true. My prior beliefs are meaningful, useful, and the new data is also useful, it's meaningful, and I have to deal with both. And the idea is that what you end up with is an updated belief. Now, so this level of reasoning is really good because it helps us to define a solution space. I've been using this word, solution space. And so I really want to talk about what it looks like to use Bayesian reasoning to define a solution space. So I've got a little Bluetooth speaker here, and it's good for a three-dimensional solution space. So if we think about our Bayesian reasoning, our prior knowledge, and in terms of ranges of say three different variables or adjustment factors. Maybe I've got on this plane, I've got gross living area, then maybe site size here, and maybe condition over here. So if I look at the possibilities, the span of possibilities between each solution space. So what is that range of possibility, of possible adjustment sets? Well, the cube, the shape here, is going to contain all of those solutions. All of those adjustment sets are contained within this cube. So what we're going to need to do is define that solution space. Now, when we get beyond three adjustments, it gets really hard to visualize. But if we just stick with three for right now, you can really see that, okay, I've got three adjustments that I've applied constraints from my prior beliefs. And now I'm going to use my data to help me to explore this solution space. And we're going to talk about next time what it means to explore a solution space. So the most explanatory set of adjustments may be in the solution space. Hopefully, if your priors are reasonable, then that will be the case. So how can we explore the area, the cubic space in a three-dimensional example like this? How can we explore that? And when we begin to explore that, then we have the problem of the other type of infinity. We have continuous infinity. We have point density within this object, and we have to learn how to deal with that as well.